I'm just gonna get started because who knows? So yeah, hi, I'm Brecht from Taiko and Gwyneth, which might be a little bit confusing. But yeah, so today I'm gonna just talk about like how we will actually integrate like the preconfirmations. The preconfirmation work is mostly done by other projects, and we are basically kind of like mostly integrating it. So yeah, talking about like how we do preconfirmation on the Taiko side, and also how we will be using preconfirmations on the Gwyneth side. So yeah, a little bit more like background information about Taiko. So a couple of months ago, we launched, it was the first based rollup. I think it's still the only based rollup currently live on mainnet. And so Taiko is a based rollup, but we don't really take a lot of advantages yet of kind of like being a based rollup. So yeah, we have like the, well, live censorship resistance properties, and also kind of like the decentralization thing. Although we are still kind of like still posing most of the blocks ourselves. But the last couple of weeks, we are actually seeing other people. Oh shit. Oh no. Okay. So we're seeing like other people kind of also like proposing blocks, which is great because otherwise, what's the purpose of being a base rollup if you're still like kind of like centrally proposing all the blocks? So that's nice. And yeah, so that's kind of like what Taiko is now, and the thing we are working towards is kind of like taking advantage more of being a based rollup. So the biggest advantage of being a based rollup is kind of like the synchronous composability aspect of with L1. So that's kind of like Gwyneth. Gwyneth will be like a horizontal scaling solution, and we'll be able to like synchronously compose between all the L2s, but also the L1, which will be pretty cool. So currently, we still only have like a TE proof on Taiko. So it's kind of like SGX. As always, the ZK proof will be coming soon. But this time, it should actually be pretty soon because we've done some tests, and like the costs should be like pretty good for proving like most of the, well, at least initially, probably like around like 30% of the blocks, and then gradually increasing from there. And this works. Okay. So yeah, I see there's some activity. So we see like quite a high number of transactions now on Taiko, which is great. But also it's kind of like incentivized. So a lot of people are doing like quite kind of like just like random transactions to kind of like get some of the incentives. But at least it is being used and like the system being tested. And like yeah, one of the downsides currently of our base rollup is, well, the costs per putting a block on chain is quite high. And there's like two reasons for that. Is we cannot wait until like yeah, to batch like as much as possible, because if we do, then somebody else would front run the other person. And so that's kind of like why the aggregation kind of like part is less optimal than like a centralized sequencer. And the other kind of like problem that's not so based related is that pushing a block to Taiko is quite expensive. So we do like a lot of work in the proposed block, the proof block, and so in total, I think like now the gas costs per like block is like 300,000 gas or something, which is quite high compared to other L2s. So yeah, we are trying to like improve that. Okay, so why do we want like preconfirmations? Yeah, obviously preconfirmations give like faster finality, much faster finality for us, because otherwise we are limited by the L1 block times. So the best we could do for users is normally like 12 seconds. On average, we are doing like one L2 block per, like a one L2 block per like two L1 blocks. So around like 20 seconds like finalization time for users, which compared to like other L2s is not great. And then yeah, also like the efficiency aspect. So the more we can actually aggregate the L2 transactions, the cheaper it will also get for users. So it's kind of like both for users, the costs aspect, and also the user experience aspect. So like I said, like we are mostly like working with other teams to kind of like make these preconfirmations live on mainnet, hopefully in the next couple of months. So we are doing the integration, and like the projects I listed there are kind of like the main projects that we've been working closely with to get like these preconfirmations on mainnet. But there's like many more. But these were like yeah, worked like very closely with. Some of them we gave grants to, and the other ones like just like nicely closely working together. So yeah, so like on the high level, kind of like how will the preconfirmations work in Taiko? This is like a very neutral slide, so it doesn't leak any implementation details. We are like very neutral normally, maybe a little bit too neutral. But yeah, so on Taiko, the preconfirmations will be like an L1 inclusion preconf on L1, and then we can do execution preconfirmations on L2. And so the only actual part that is Taiko's, like we actually built into Taiko is kind of like the registry contract to see kind of like which preconfirm is actually selected for a current block. And then, yeah, I guess that's basically it. So the other parts are kind of like up to the implementation of the preconfirm, and we do not currently set any kind of like, we don't control that. We might in the future like require a proof of like how the block is being built to kind of like have more control of like how preconfirmations are given. But currently that's not currently like that. So like on the Taiko side, like what changes did we have to do to actually get like preconfirmation support is just to make our block proposal was kind of like non-deterministic, as in if you proposed a block, then the L1 state that was injected into L2 was always from the previous block. So you could not predict more than one block in advance how the block will actually execute. So we just had to make that more deterministic, that it was like the preconfirm can actually specify which L1 state is available to the L2. So that makes it possible for the preconfirm to actually give execution preconfs, because the full execution needs to be deterministic at the time the preconfirmation is given. And so, yeah, it's kind of like more of like the L1 block state available to L2, like the timestamp, kind of like difficulty stuff. That's kind of like mostly it. And yeah, the other kind of like thing on the side is kind of like, yeah, how do we actually give these preconfirmations for users that they actually see that they got the preconfirmation? And that's kind of like where we have to be able to create like a lot of like blocks, because the wallet then sees there's a new block, and then they see that their transaction was actually confirmed in this block. So that's kind of like the thing to be compatible with existing wallets. Yeah, they just have to have like a wallet, a block, so they can see like, okay, this transaction was included in the block. The transaction is like pre-confirmed. So that works well. I guess the only problem there is that creating blocks is quite expensive currently in Taiko. So that will be solved in like Gwyneth. And the other problem with like preconfirmations is, well, yeah, the opt-in. So people have to opt in. If there's like another opt-in, then we have to use like a fallback path, which is still fine, but less than ideal. And also like the preconfirmation duration. So the more preconfirms there are, the faster they switch, which is good for censorship resistance, but it's bad for aggregation. So the faster they switch, the faster like an L2 block needs to be published to the L1, and that means that the L2 block can be less big than normally. Okay, so base rollup efficiency. So kind of like that. What the question then is like, how efficient can we actually make it? So yeah, if you just give the preconfirm like a larger window, then they can do more batching, but it's bad for censorship resistance. And also like how long should you actually give the preconfirm kind of like this window? So Connor actually came up with like an improvement on that, where the preconfirm can actually say like, I want to at least these amount of like slots, and then they can batch within these slots to be able to create like a big L2 block. But still, that means that they kind of like have to predict how long it will take to build like a full block, and yeah, that might be like hard, and there might still be like partial blocks at the end. So you might be able to build like a big block, but then still have to create like a smaller block at the end. So this is kind of like a way, it's still kind of like hand wavy, as in it could work, but so you could actually do the preconfirmation software in like a TE, and then basically define like how the block needs to be built. And then you can make sure that you can kind of like chain the preconfirms. So if there's like a partial block for preconfirm A, this preconfirm would be able to send those preconfirmations to preconfirm B, who would be required to actually accept those preconfirmations. And then in return, there would be kind of like some profit sharing mechanism, so that, yeah, this actually would work. Because the preconfirm B, who needs to do these preconfirmations, actually has like another like upsides of doing this, because, yeah, these are preconfirmations done by somebody else, so he doesn't get any profit. And yeah, kind of like loses block space, because those preconfirmations will also like take up block space. So yeah, to be able to kind of like set the incentives correctly and also to do the profit sharing, yeah, you could run it in TE, and then yeah, just define, okay, this amount of profit was actually made, and then kind of like share between those preconfirmations. So something that could plausibly work, but I think like more work needs to be done to actually do it. Okay, so this is the Taiko site. So now a bit more about Gwyneth. So yeah, Gwyneth is basically well, also like a based rollup, but with more features that, like I said, like actually make advantage of like being based rollup on top of horizontal scaling plus like synchronous composability. And obviously, we also want to support based preconfirmations. The thing is that for L1 synchronous composability, you have to have like immediate proof generation. So compared to Taiko, Gwyneth can only support real-time proofers, which currently means TE or AVS or a similar kind of like proving system. Once ZK is available, then we'll also be able to use ZK. Any moment now? Oh, okay. So yeah, when it's horizontal scaling solution, so the idea about like booster rollups is that you would be able to just deploy your application on L1 once, and then all the L2s would directly be able to access that application. So you wouldn't have to, like if you want to have like Uniswap on your L2, the Uniswap would only have to be deployed on L1, and then all the booster rollups would be able to use that application in the same way. So to actually add capacity to the network, yeah, there's like no extra kind of like work for developers. You just like add this L2, and then automatically you have like more storage, more processing capabilities. So that's kind of like the idea. So like one smart contract at the top, all kind of like organized by the L1, and then multiple like instances on the L2. And like additionally, because deploying to L1 is expensive, so for things like smart wallets, where users would actually just like, yeah, a smart wallet, they only want to deploy once, they don't want to have like the high costs to be able to deploy to the L1, and they are fine with just being on a single L2. That's why you also have like the colored smart contracts where they are actually just available on those L2s. But yeah, in general, for applications, you just want to be available everywhere. So yeah, quickly about like how Gwyneth blocks works. So a block would basically be like a super block. So the super block would contain transactions for all the L2s. Then builders kind of like build this kind of like super block. So they have access to all the state while they are building it. So they kind of like merge all the chains together. Then they prove the block. And then we can like prove it in a way that then decouples all the transactions between all the different L2s. So that means that if you actually want to sync a single node, you are still able to do it. So there's like no interdependencies on the syncing level. There's only interdependencies on the building level. So that means that, yeah, builders have to have higher hardware requirements, but still syncing like a single node is very easy. And also builders will just be able to pick which nodes they want to sync to be able to build blocks for. So that's kind of like the main system is kind of like an opt-in system where builders can kind of like optimize for access patterns and also kind of like which chains they actually want to build for. So even if there are like thousands of L2s, they can just select the ones they want, sync them, and then build blocks for them. So yeah, so on the pre-confirmation side is, well, if you don't touch the L1, then it is as easy currently on Taiko. So there's like, yeah, nothing special that needs to be done. Also, if you have like a super transaction that touches like multiple chains, it's still a single pre-confirmation because the user only has to sign one transaction, and that one transaction will kind of like touch all the necessary chains, but there are no actual multiple transactions that need to be signed. So one pre-confirmation, one transaction. So easy, nothing special to be done. The difficulties are when you actually want to have like synchronous composability with L1, or at least like read access to the L1, or anything you actually want to do with the L1. So yeah, just to kind of like make it clear that to do L1, like a L1, L2 synchronous composability, there is actually nothing special that is required to be able to do this. So you don't actually have to be like a base rollup. You just have somebody that kind of like organizes the whole building process for the L1, and then just includes these L2 blocks at the right location. So you could like a scheme that you could do to do these kind of like things is just to say, okay, my L2 depends on this specific L1 state, and then in the smart contract you check like, okay, has this L1 state, like is the L1 state as expected, and then you kind of like use the normal PBS kind of like revert protection to either include it or not. So that's kind of like how you would be able to do synchronous composability, just like in the current like PBS pipeline. So yeah, so for example, builder A would build like a certain L1 block with L2 blocks. There's another builder B that creates like another L1 block with other L2 blocks. And then again, they go through like the normal PBX auction, and then one would be selected, which is fine. Like you have synchronous composability in either of the blocks. You just simply don't know which one will win. So the problem is then like how do you do this actually on? So actually, if you want to be able to provide execution preconfs on L2, then you do need to know like which one of those will actually end up in the L1 blockchain. So to be able to do that, the L1 validator needs to be somehow involved. So either like a super builder, and then like well, basically in theory, the L1 validator would build the whole thing themselves, or like in practice, there would be like an execution preconf on the L1. So yeah, L1 validator gives preconfirmations, execution preconfirmations for like the L2 proposed transactions, and then you can actually just easily make it work. So compared to like the Taiko way, so it's kind of like a nuanced difference. So there's like 3 L1 blocks there, and on the Taiko case, you could actually do aggregation across like all these 3 L1 blocks, and at the end, kind of like include the L2 block in the L1. If you do want to have like synchronous composability, then you cannot actually use kind of like the intermediate L1s that are not the actual preconfirm. Because if you want to have like the synchronous composability, then like only this L1, like the preconfirm that is actually the L1 proposer, can actually provide you this execution preconf. So there is less batching possible in this case, and like the amount of slots you can actually do it is much less than before, because only opted-in preconfers would actually be able to do this. So I think that's all what I said. So you just still have to make sure that whatever L1 state you used on L2 actually matches what you wanted to do. Even though the amount of like state required to do that might be low, so kind of like on the builder perspective, the amount of like state you actually have to lock is kind of like could be like quite small. So it might be less of a problem than you would think. But still some practical considerations to actually do it. Like I said, only actually opted-in L1 validators that actually give execution preconfs would be able to actually do this. So this is kind of like just something that I find interesting, which is slightly related to like the synchronous composability with L1. It's kind of like how you can actually optimize kind of like read access from L2 to L1. So if you want to read some state from L1, like how do you get it to L2? The most naive way would be, okay, if L2 actually requires some L1 state, you just read the necessary L1 state before you do the proposed transaction, so you know it's the latest one. Then you inject it to the L2, and then on the L2, whatever L1 state you need, you just get it from the inputs that you just got. That means that you have to read it on L1, which is expensive because S load is like 800 gas. And it might actually not be possible for kind of like the rollup contract to access the data in the smart contract because of like state access limitations on the smart contract level. So it's not like this is a good way to do it, but inefficient and maybe not possible in all cases. Then the other way is to just make sure that so the state root of the previous block is available in the current EVM block, is available in the current block exposed to the EVM, because the previous 256 block hashes are exposed to the EVM. So you can get the state root from the previous block. And so if you then just build on top of that state and you know you're in the first transaction, then you are sure that you're also accessing the latest L1 state. But that also means that to be able to verify this is correct, you have to know in your block, in your transaction, that you are the first transaction in the block. Otherwise, you cannot verify that you are actually reading the latest state. And you can actually do this. You can actually check in the EVM that you are the first transaction in the block by using like a trick where you set like the transaction gas limit to the block gas limit, and then the first thing you check in the smart contract is kind of like my gas left is kind of like very close to the block gas limit. So this is kind of like cool that it's possible, but there's also like an EIP that kind of like exposes the transaction index in the making, which is hopefully also be available soon. And then, so this would only work for the first transaction in the block. So if you want to generalize it and just like, okay, I want to have like, make sure that I have the latest state anywhere in a block, then you need like additional EVM functionality. And so there's like, I made like an EIP that allows you to do this. And basically it just allows you, it basically exposes to the EVM the current transactions that are done in the block. Because currently that's not available. If you are like a transaction in the block, you have like no idea which location you are or what transactions came before it. And so this EIP would expose this. And then knowing the previous state root plus the transactions that are currently in the block, you would be able to execute, recalculate the current state of L1 on L2, and then have cheap access to the L1 state. And that's kind of like the whole kind of like point of like booster rollups, where you have like this L1 state available like very cheaply to the L2, so you don't pay any L1 gas costs to be able to read from read L1 state from the L2. You just have like normal L2 gas costs to do it. Okay, this is just like a normal example, but yeah, just like to make clear like how this kind of like synchronous composability thing works is if you would have like a normal like smart wallet on L2, then basically the smart wallet would be able to just go between all the L2s and the L1 to kind of like make it work. So if you have like a key store smart wallet and you store all your like addresses that are the owner of your smart wallet on the L1, you just read it directly from the L1, check if it's correct on the L2, do whatever needs to be done, a swap in this case, and do like the token transfers. So for the user, it looks like a normal transaction. All these things are just handled internally in Gwyneth. And yeah, I guess that's the main goal of Gwyneth. It's still like Ethereum organizing everything, and for the users, it kind of like just looks like a single chain, and everything works well, and everything is based, and it's just as ideal as possible. That's it. Questions?
In the EIP thing that you mentioned, you say that you expose enough information to calculate the L1 state root in the L2. Does this also mean that you have to, like, in the proving stage, you have to prove the whole L1 execution?
Yes.
Okay.
Yeah, you have to re-execute everything on L2 of the same thing that happened on L1. Yeah.
I see. Okay, thanks.
Which is a certain extra cost, obviously. But yeah, the extra cost for proving, you assume it to be much lower than the actual like execution cost on that one.
I see. And I guess you guys already have a EVM execution prover, so it doesn't make that much of a. You guys already have a prover for the.
Yeah, exactly. For us, it's very easy because it's just the same, basically the same thing we're already running the prover for. Yeah.
I see. Makes sense.
Okay, thank you.